Hey everybody, Dr. A here, and in this video we're going to be providing some background information on friction for the purposes of a statics course, and we're going to be referencing the Hibbeler Statics textbook. But before we dive into it, don't forget to hit like and subscribe and be on the lookout for other content like this. All right, let's get started.
In this video, we're going to be discussing sections 8.1 and 8.2, which is on friction. Now, in the textbook, these two sections have a lot of background information, a lot of large paragraphs to read. So I'm just going to be summarizing the content of a lot of this text-based material from sections 8.1 and 8.2, but I strongly suggest that you take some extra time on your own and read through 8.1 and 8.2 in a little bit more detail, because again in this video it's just going to be kind of hitting the highlights of the content in there, but you need to look over all of it in a little bit more detail. So what is friction? Friction is a force that resists movement of two contacting surfaces that tend to slide relative to one another. So the classic friction problems that we're used to seeing are a block sliding along a surface, and that surface may be a horizontal surface or an inclined surface, which we often call in physics block on a wedge, okay? And more specifically, what we're going to talk about is this thing called dry friction. So dry friction is typically what you have also studied in a Physics 1 course, and that occurs when there is no substance in between the surfaces that gives some kind of lubrication to increase the sliding capability and decrease friction. So we're talking specifically about this case of dry friction, which is also known as Coulomb friction, which is named after a mathematician and physicist with the same name. So let's give some background on this. So in general, we can model this as the following. When a force P is applied to a block with weight W, a non-uniform normal force distribution will develop at the base on the contact surface, and also a non-uniform friction force distribution develops. So what do I mean by this? Well, let's look at an illustration. Let's say that we have a surface here, and here's our block, okay? And let's say that we have this force P applied to the block, and let's say the block has a weight of W, okay? So as we apply this force P on this block is going to want to move in the direction that P is being applied. So in this case, to the right. And when that happens, two things are going to develop at this surface of contact, okay? One thing that's going to develop is this non-uniform normal force distribution, okay? And we're going to call this delta N, all right? But simultaneously, what's going to develop is a non-uniform friction force distribution that will develop that tangent or parallel to that contact surface. And I'm going to call this delta F sub S, okay? Now, what we can do is we can resolve these force distributions as the following. We resolve these normal and friction force distributions as the following. So we're going to take that same surface here, and we have that same block, okay? And of course it has the same weight, same system. And then we still have P here. Let's go ahead and say P is applied at some height H. I could have put H here at this on the original figure as well. And so when these force distributions are resolved, we're going to get this normal force developing here and a friction force, F sub s, developing here. Now notice that the friction force is pointing in the opposite direction that the block is wanting to move, okay? And that's what we commonly know as friction. It's a force that develops that opposes movement, okay? Now, one thing we need to notice is take note that this normal force is not on the same line of action as the weight W. In fact, they are deliberately a little distance away from each other. And that perpendicular distance that these two lines of action are away from each other, we're going to call this distance right here. It's this distance in between right here. We're going to call that distance x. Distance x right here. Okay. Now, we can develop a resultant force as well. We're going to have this resultant force develop right here. And guess what this resultant force is a result of? Well, this is the resultant force of F sub s and n. So it's basic vector mechanics like we've been dealing with a lot in this class. Now, what's interesting is we're going to have this angle that develops here, and we're going to call this angle phi sub s. So if we looked at a free body diagram, of this system, we're going to have, well, not of the whole system. We're going to look at a free body diagram of just this portion right here for now. But we're going to have n. We're going to have F sub s. Ooh. In fact, let me move my n to the other side here. And we're going to have this angle right here again. That's phi sub s. So phi sub s is an angle that's in between this normal force, this vertical normal force, and this resultant force right here. Okay. Again, why is there a distance x here? We would sometimes ordinarily want to think that W and N are lying along the same line of action, but they're not. Why is that? Well, the distance x arises due to the non-uniform normal force distribution. Remember, we drew that original distribution. This is non-uniform. It's got some kind of non-uniformity to it, which pushes the resultant force of N off center from the resultant of W. Okay, so that's the general background of it. All right, now when we're dealing with systems like this, we have a case of what's called impending motion. And so we think of impending motion versus motion. Impending motion has to do with being on the verge of motion. Okay, so that means motion is impending. It's about to happen. So let's talk about that. Okay, I'm going to change colors here. I'm going to say impending motion. Okay, so how does this occur? Well, if F sub s, that friction force, is not great enough to balance the applied load P, the block will slip. So think about that. If the friction force, remember the friction force is resisting movement. If the friction force is not large enough to balance the applied load P, that means the applied load P is bigger than the friction force and the block will tend to want to slip. Okay? So the maximum value of F sub S before slipping is called the limiting static friction force. And what is that? Well, that's going to be F sub S equals mu sub S times that normal force. Okay, now this should be a familiar equation to you. We often cover that in a Physics 1 course. And we're going to say where mu sub S, mu, that's the Greek letter mu sub S equals the tangent of phi sub S. So think about that for a second. We're saying that the tangent of this angle phi sub S is what mu sub S is. Okay? Now, another way we can write that is the following. We can say phi sub S equals arctan of mu sub S. And guess what we can also say? We can say phi sub S is equal to the arctan of F sub S over N. Where in the world am I getting arctangent of F sub S over N? We'll look at our little partial free body diagram here, okay? If we have this resultant force here, and we have a normal force here, we can build a right triangle right here, okay? And then we say tangent of phi sub S equals, guess what this, what is this horizontal measurement down here? The same thing as that horizontal measurement is F sub S. So phi sub S is equal to the tangent of opposite over adjacent, which means that phi sub S is equal to the tangent of phi sub S is equal to opposite over adjacent, which means that tangent of phi sub S is equal to F sub S divided by the normal force there. Okay, I think I said a couple of extra words in my explanation, but that's it. We build a right triangle out of this, all right? So let's talk about motion now, okay? That was impending motion. What about motion? Motion itself, okay? So if P increases to a value larger than F sub S, the friction force at the contact surface will drop smaller and become F sub K. And we call this kinetic friction force. F sub K is the kinetic friction force, okay? And then the block will slide, all right? And we say the kinetic friction force is equal to mu sub K times the normal force N. So essentially, mu sub S becomes mu sub K whenever the applied force P exceeds the frictional resistance F sub S, okay? So again, as I mentioned before, you need to read sections 8.1 and 8.2 because I'm just bullet pointing it for you here. Those sections are gonna go into a lot more detail, okay? So what we're gonna consider for this course are three different cases involving our classification of problems, okay? So we're gonna say problems in dry friction, okay? We have three classes of problems. we have no apparent impending motion. The second class is going to be impending motion at all points of contact. Okay? And then the third case is going to be impending motion at some points of contact. And in terms of problems in this course, you just need to read the directions carefully and figure out what the directions are telling you about what type of potential issue you're dealing with in a given problem. So let's talk about each one of these very quickly, okay? So let's talk about the first case, no apparent impending motion. Okay, in this case, these are just static equilibrium problems. Okay, and we're going to say F is less than or equal to mu sub s n holds true. So that means any force that develops is always going to be less than the friction force, right? Mu sub s n is the friction force. So any developed force will be less than or equal to the friction force, which means that it's not going to move, okay? And then we need to make sure we investigate all contact surfaces to make sure that this second bullet point is holding true, okay? Now, what about the next case? We have impending motion, and then we've got all points of contact. What do we mean by this? Well, in this case, we're going to say the total number of unknowns equals the number of equilibrium equations plus the number of friction equations. So in this case, when all the points of contact in a system are experience impending motion, that means that you have several unknowns, but the number of unknowns you have is going to be equal to the number of equilibrium equations you have for that given system plus the number of friction equations. So what do we mean by number of friction equations? Well, remember, at each point of contact, you're going to have a friction relationship, right? F sub s equals mu sub s times the normal force at each point of contact, okay? So that means that we're going to say at each point of contact, we have F sub s equals mu sub s times n. Okay, so those friction equations will give you the additional necessary equations you need to solve for all of the unknowns. Okay, and then the last classification of problems is going to be impending motion, some points of contact. Okay, now in this case, we're going to say the number of unknowns is less than the available equilibrium equations plus the available friction equations. And then we're going to say motion may occur at some points of contact, but not all. Okay, so this is, again, a bullet point summary. Take a look at sections 8.1 and 8.2 and read those paragraphs.